Hi, my name is Rayo. I'm an A-level physics and math teacher. I've been teaching for almost 10 years. I used to major in automatic control in Beijing University of Aeronautics and Astronautic. I started to teach since college. I have a passion in science, like the mighty power or the mysterious magic. I believe there's something in there and even more, the other and the beauty. So now I'm putting my passion in teaching this and sharing with my students. My students went to the university like G5, like Imperial College and UCL, and quite a few of them went to university at this level. So now I'm starting to share a little bit more about what I learned today. Terminal velocity. What do we know about terminal velocity? We learned it in IG, right? We're going to learn it again a little bit more. So we know like terminal velocity is because of the air resistance, right? So this is what we have to learn in syllabus in ES. And of course, the example is not this. Air resistance is this example. But we're going to learn a little bit more about air resistance in terminal velocity. What's related to this force? So there is a force in here if you drag all the way there, right? For example, if I have a car in here, say I have a car. So this kind of car is gonna be, well, wow, it's kind of broken. So when we see cars like this, we don't assume they run very fast. What? It's because the shape, huh? It's, well, we use the word common sense like a smooth. The shape of that looks like it's a fast car. So, and if we require the data, we can see that surface area. That's something related to the air resistance a little bit more. And what else? Velocity. So for example, faster, higher speed, you can feel the wind a little bit more, right? If you go slow, yeah, your arm doesn't really feel that much, right? So more velocity, more drag, right? This is what we learned before. And now density of the fluid, or density in this picture is density there, right? Or density, you imagine if you do this like a submarine, like underground, in the water or in the oil, that'll be different, right? Which means more density. You can imagine if there's more molecules in there. If you try to go in there, oh, there must be more air resistance, right? So all of this kind of factor is going to relate to air resistance a little bit more. So we're going to talk about a formula we're going to see, but in S, we're not required to remember this. So this is going to be related to the density, right? Your drag, this is going to relate to an area too. And also velocity square, actually, is going to drag is going to be your proportional to your v squared. And this is the formula they're going to provide. We don't have to remember it. So that's why they use it to, deduce all the units. C is constant. This C is just the coefficient of this kind of situation. This coefficient of this kind of drag. And we're gonna learn a little bit more. So we talk about this like in like a skydiver or like a parachutist, right? So they use parachute and they have a person in here. So what we do in here is sometimes we provide a formula. So we can do a little bit more like a resultant force. So we know there's drag and there is gonna be my air resistance, right? And if they balance, that's terminal velocity. That's what we learn in IGCSE, right? Well, the flow phenomenon is this. You're jumping off of the airplane, right? You're jumping off the airplane like this. Let's say this is the airplane that carries this one. It jumps. And then in the beginning, what you actually feel is not that friction, right? In the beginning, this is the mg, you feel a little bit or nothing, right? And later, this one, because more velocity leads to more drag, right? So which means this is going to be getting higher and higher. Eventually, they're going to balance, right? This is called, when they balance, you have terminal velocity. And the graphing velocity time will be looking something more like this, right? Your speed is getting faster and faster, but your acceleration is, well, in the beginning, it's kind of like because the air distance is small. So it's kind of like a linear in this situation, right? And then when it flattens out, it's actually because this one is increasing, so the resultant force is decreasing, right? Resultant force, R resultant, F resultant, F resultant, F resultant, F resultant. It's gonna keep decreasing, right? Until eventually F resultant is zero, right? This is F resultant is zero at this point. This is 2, it's totally balanced in situation like this, right? So this is what we learned in ADCSE. And now, let's see. We now know the drag force, like a drag equation about this. And they provide for, we don't have to memorize this in here. And sometimes they give you the drag in a different, maybe a lower speed, is like a kV. But this time is like a proportionate to k. This is proportional to v squared. But they're gonna provide, it's okay. We're gonna take some example later. So let's see, who has the greater resistance? We say this guy definitely has greater velocity because he is down a little bit more, right? So since the velocity is more like this, right? The velocity is more like this, so it's gonna be more resistance in here, right? So there will be less resistance in here. So that's why you see the red is a little small, right? And here red is a little bit big, right? Because you have more velocity. And of course you have the result for it. Let's see about the data in here. I love the data in here. So in the beginning, we're gonna have 0, right? T equals 0, velocity is 0. A, almost no friction. And then later, a little bit more friction, more velocity. So you're gonna have a decrease, right? See, a decrease, 6 decrease, and 2, and then 0, right? Bingo, that's where you have your terminal velocity in here, right? It starts in here. It still go for all the way in here, right? So take a look at the real example that we have to deal with this in. Yes, if you ask me, not much difference. There's a little bit more detailed about the forces and about the formula a little bit, but they provide the formula. We don't have to memorize. So this is the terminal velocity. Eventually, air resistance balanced with the weight, right? And that force, of course, is 0, acceleration 0, velocity constant, terminal velocity or terminal speed. And same thing as this parachutist, right? This is a real example. See, we're gonna skip the first 2 questions since we focus on terminal velocity here. Here's the parachute is falling off from an aircraft, which is just the example that we talk about. Oh, I love this picture. I can totally draw all this. See, I can draw the force diagram is always a key in this kind of situation, right? So in here, let's just say there's almost nothing in here, right? And in here, you have a little bit more, right? Let's just say this one is in here. You have a little bit more, right? In here, you have a little bit more, right? And the drag is a little bit more. A little bit more drag in there. And in here, your drag is totally gonna balance, right? Yeah. And in here, what's happening here? I think here is parachute opens, right? Well, you can't keep this forever and until you hit the ground. That will be catastrophic. So in here, I can say dramatically, because the parachute opens, you have a huge drag. And in here, and your drag is also going to decrease a little bit, right? Because your velocity is decreasing, right? Your velocity is decreasing all the way in here. So your drag is also going to decrease in here. And it's still higher than the MG, but eventually in here, it balance again, right? But this time in here is actually kind of decrease, right? In all this is kind of decrease and you balance. And this is all you increase and you balance. And that's a little bit different. And here is the terminal velocity. Here is also another terminal velocity, right? To talk about this situation in here. Calculate the distance traveled by the parachute is in the first 3 seconds of the motion. And this is 10 and 3 seconds. It's around, well, 10 over 3. I believe it's in here. Oh, I guess I have to find the units. It's kind of tricky. This is 25 units, right? I like to use a ratio table these days. So now I have how many square, a little square? 25, right? 10 here, 10 here, 5 here, 25. And represents 10, right? Scale. And then I have to say, I want to say, what if it's 1 little square? So it's x, right? So x over 1 is 10 over 25. So x equals to 10 over 25, which is 2 over, is it 2 over 5? Yeah, 2 over 5, right? 2 over 5, 0 0.4. So, oh, I think it is here. If that's there, it's going to be half 2.5 in here. So it's half in here. I believe it's half in that. This is 29. It is half 29. A little bit more than 29, which is 29.5. So 1 over 2. So this is totally the area, right? This is the area of this little triangle. 29.5, right? It's 29.5, 29.5. And then time that 3, right? And this is going to be the meter in there, right? This one. And then explain the variation of resultant force acting on the parachutist from t equals to 0 to t equals 15. And this is 0. And this is 15. Where's 15? Oh, they tell me 15 C. Great. C is in here, right? Oh, that's 15. Is it 15? Oh, I think it's in the middle, between 10 and 20. So what's happening? Say first, resultant force. In the beginning, as we said, in the beginning, there's only mg, right? In the beginning of resultant force is mg. It's gravity. Because their drag force is 0. And the second is, well, let's say, I don't want to say second, I want to say the end. The end is easier. The end is our terminal velocity, right? So you're going to balance, your gravity is going to balance with your drag, right? Not like just purely alone. So at that point, your drag is mg, so your resultant force is going to be 0 because drag equals to mg, right? And then 2 is in the middle, and I guess your velocity increase, which leads to drag also increase. So the resultant force is going to be decreasing, right? Decrease. Well, because this one is getting larger. And the acceleration is decreasing. Well, they didn't ask us. Let's say a little bit more. Describe the change to the frictional force on the parachutist at t equals to 15. T equals to 15. Oh, that's when parachute opens, right? So now parachute opens. Unbelievable huge. So frictional force dramatically increase, right? Dramatically increase. Because the parachute opens, right? And then between 15 to 22. 15 C and 22 E. I guess we ought to divide it and conquer. In this period, it's linear, so acceleration is constant, right? So which leads to F equals ma. Resultant force is constant, which leads to drag must be constant, right? So that's unbelievable huge because of the parachute, because the parachute is unbelievable huge. So first it is constant, so constant friction first, and then this part, I guess because you decrease a lot of velocity, right? As we said it's actually proportional to v squared, which means the friction dramatically decrease, right? We don't have to use it all the formula. We just say the friction decrease later, right? Friction decrease later. So that's why the resultant force decrease, right? Because in here is unbelievably huge, in there, and now you just decrease, huh? You decrease. You decrease, huh? Until you actually balance it again. And that's only 1 point, I guess that's enough. Okay. That's the last question. Oh, there's another one. Calculate the parachute between 15 to 17 and D, C and D. What acceleration? Average, the average acceleration. Let's see the average acceleration about this. C and D. If this is linear as we talk about it, then that's the slope. At acceleration, we find friction. Oh, he's not asking the friction. He's asking the average acceleration. So the acceleration is just delta v over delta t. And here, delta v is the final one is, I believe it's 20, right? 20 minus that 50. And over 15 minus 17 minus 15, so which is negative 30 over 5, which is negative 15. So I assume the velocity in this is positive direction, right? So the acceleration in that direction is going to be negative, right? So I believe it's negative 15 meters per second squared. And then next one. And the average frictional force. So here is something that I asked a lot. Before we don't talk about this kind of resultant force, right? Now let's talk about it. So resultant force at let's see, at which point? Average force between, oh, it's still between C and D. C and D. We just find A is negative 15, right? So it's only natural that I talk about a sigma F equals MA. Well, that's gonna be related to my drag, right? I guess it's mg minus d, which because this is mg, and ooh, I have to draw this one unbelievable huge, and that's your drag, right? So I believe this is positive, right? So my mg, which is did it give me mass? Oh, 95 here. 95, here is 95 times 9.81 minus d also equals to 95 times negative 15, right? Since I'm using negative positive in here, so I'm going to leave it to calculation because we know it's a vector like equation. It's going to be working. So d, I'm changing on the other side. It's going to be 95 times that 9.81 plus that 15, right? I got a common factor. So this is going to be my drag, the frictional part, right? So be careful with that negative sign. Otherwise, you have a different answer. So that's why we say this negative, positive is important. So this is positive, right? So if you have alpha direction upward, I'm going to say you are negative. Next one. Oh, next one is that proving that the units of the C, the coefficient, right? So we can just, substitute all that. And let's see, next one. Since I only want to focus a little bit more on terminal velocity, I'm going to skip a little bit to talk about, this is the ring, right? This is the ring. I believe it's the ring. Oh, the range of phosphorescent from rest. And the sketcher graph, if it's a ring, it's a g acceleration in the beginning, right? It's kind of what we had before, right? Same thing, right? So it's just 1 second, a little bit g or a little bit less than g, right? 9.81. It's constant. There is no resistance. And I can calculate the velocity in here. I can use the formula in like the big five. I'm gonna move on a little bit what we want to use in here. Because they provide me here, right? It's the equation that provide me. And then they said in practice, air resistance job is not negligible because there is a drag force. And it's given by this expression and state an equation between this when it's falling at a terminal velocity. Oh, when you terminal velocity and then drag. So I guess it's not exactly this anymore, right? It's still one of those, right? Yeah. So I guess in the end, you drag balance, right? Wait. You drag balance with this. So I guess it'll be just drag equals to mg, right? That's the equation. Right? That's the two forces. Mg, this is the drag, right? And then we can use it in here a little bit. The range of has a mass in here and its cross-sectional area in here. The density is in here and the initial velocity is 0. And the value of c is 0 0.60. The terminal velocity is 7. Well, because we just have this equation, right? Because with the equation formula that it first provided us is 1 over 2 rho a v squared and times c, which is this 0.7, right? 0.6. So I believe I can use that 1 over 2 rho 1.2. Is this the SI units? I believe it's SI, so I can just forget about the units. 1.2 on time that area is 7.1, right? Times 10 to the negative 6. And time v squared is something I don't know, right? And it equals to that, wait, I have the time that 0.6. Time that 0.6 and then equals to that mg, which is 1.4 times 10 to the 10 to the negative 5 g, which is 9.80. Which means next time you see a range of, which is also constant velocity in there, you go all the way in there, right? Basically, anything with the unbelievable large height coming from like a free job, eventually would have a big change. They have terminal velocity, right? Eventually balance. So with this, I can substitute everything and then have my v squared and then a square root, so I can find it. So that's basically what we learned today. I can leave a little homework. We basically learn everything just with more details. The larger question is just that is just this. If we draw it, it'll be more like this, right? And in here, right? And then in here, again, and in here, right? So that would be this. It's like 5 steps or 6 steps of this, right? And we have here is the terminal velocity part, right? Here's the terminal velocity part, right? And here's again terminal velocity part, right? It is unbelievable large part. And it is this more like only gravity in here. A very little more like air resistance. And then the second, we use the resultant force. With the formula, we can find the drag, right? One is that 1/2 rho a v squared c, right? The other one, sometimes they also provided kx. You just use that equation and make it into Newton's second law, sigma f equals to mg minus drag, right? This is what we learned today. I hope we can find all kinds of like terminal velocity in a lot of things. A lot of things drop, right? A little dust, a little rainbow, like parachute, or like what coffee filter ring, or a little like this, right? If I live it like a little tissue, if you go like a skyscraper and live in there, if it can drops without wind, yeah, somehow it probably have that too. We will learn in so many other situations. We also have a big chance, even including missiles or cars, right? We also have a big chance to have like a terminal velocity. In liquid too. Let's leave a little homework in here. Page. What is page 52? Page 52, question 7 and question 8. And one is the different period of that terminal velocity thing, and then the other one is using the formula to find resultant force. Question 7 and 8. I believe that's it. I will enjoy a little bit more about this.